Okay, we've survived everything up to now. Let's take a look at chapter 9. New stuff. So notice we're estimating something. We're estimating a population proportion. It's the first time we've really done this. Now we know we're going to, use techniques we already know, but this is the first time we've really done this. So here's what's coming up in chapter 9. We got sections 9.1, which we're going to look at today and tomorrow, and section 9.2. Tomorrow being next Tuesday, now that I think about it. And so then next Wednesday and Thursday, we'll look at section 9.2. And so what are we doing in this chapter? Well, here's the overview right here. We're trying to answer one of two questions about the population now. Like it says here, what percent of Americans think we didn't land on the moon? Well, there's a certain percentage that believe that. Will we ever know what that true percentage is? No. No, we won't. Or what's the average weight of an American bulldog? Will we ever really know that? No. But we're going to try and estimate it. Now notice one of those is a proportion and one is an average. And so here's how it breaks down. 9.1 is dealing with proportions. 9.2 is dealing with averages. And like it says here, yeah, we're going to be using samples to base our guess on. Well, that makes sense. We've been talking about samples since day one of this class. So we're just taking a guess. That's what statistics is, taking your best guess based on math and data. Okay, so we're going to start with 9.1. So we're looking at a population proportion. And there's certain steps we're going to do. Here's the first one. This looks familiar. So our sample has to be random. That's one of the requirements. If it's not, all bets are off. We might as well just throw a dart at something for our guess. Next thing, what do you think it might be? What looks familiar? So we're going to find p hat. In other words, if I have a sample of 100 people and 40% of them believe in the Easter Bunny, then p hat would be 0.4. We're going to build a net. Now notice net is in quotes. It's a conceptual net. And the center of it is p hat. This will make more sense in just a bit. Well, how wide is the net going to be? I could throw out a short net or a wide net. I've got my choice of how big that net's going to be, believe it or not. Now, when I use words like capture, remember what we're doing. We're trying to estimate some population proportion. So I want to be in the ballpark of where that thing can be. I can't pinpoint it exactly, but I can tell you, well, I think it's between this and this. And that's what we're trying to do. That's what this is all about. And just a reminder, how do we get p hat? It's x over n, yeah. And x is the number of things in our sample that match up to what we're looking for. So if we're looking for people that believe in the Easter Bunny, that's what x is, the number of people in our sample that believe in the Easter Bunny. If we're looking for the number of people that wrote in Homer Simpson's name in the last presidential election out of our sample, that's what x would be. Make sense? So far, we haven't made a guess. We do know, though, that p hat, what are the odds of it being exactly what the population parameter is? Pretty small. Pretty small. Okay, you can laugh at my little graphic here if you want to. If you do it without me seeing you, that will probably make me feel better. But this green thing is our net. We're trying to capture Nemo. Oh, don't give me that look. Now, Nemo, what is Nemo? Nemo is that population proportion that we will never know. I want to be able to say, though, it's between this percentage and this percentage. If that net captures Nemo anywhere, it could be way out on the edges. I've done my job okay. Remember, we're just taking a guess. We'll never know if we're right or not. Okay, let's keep going. Don't write this down. This is in the textbook. What we're doing here is called a confidence interval. We're getting an interval with a left-hand endpoint and a right-hand endpoint. And we're saying, we think our population parameter is somewhere in that interval. It's called a confidence interval. What's it based on? Well, in this case, p hat. If you look back here at this thing, p hat is right in the middle of our net. So we're going to decide, well, how wide do we want that net to be? And that's what's coming up in just a minute. Okay, we've got the confidence interval, and we've also got a confidence level. In other words, how sure are you that Nemo's in that net? Because we can't look and see. Look what it says. Now, please get this in your head. The level of confidence is what? The expected proportion, okay, that will contain the parameter if we do this sampling over and over and over and over again. Now, we're only going to do it once, but if we did it thousands and thousands and thousands of times, our level of confidence is what proportion of those times would actually capture that population parameter. This will make more sense. Just trust me on that. So, for instance, if we're talking about a 95% level of confidence, then that means out of every 100 times we did this sampling, 95% of those times we would have captured that parameter. If I've got an 80% level of confidence, that means out of 100 times of doing this, we would capture that population parameter 80 times. Why the difference? Well, some of it depends on how wide our net is. You stop and think about it. If I throw a really wide net out there, I'm going to be pretty confident that I capture it. On the other hand, if I throw a really short net, my confidence level goes down. So these are tied together. Okay, what do we need to have for this to work? First thing, the sample has to be random. That's a requirement. Is this any different from the chapter 8 stuff or the chapter 7 stuff? Not at all. When we started the class off, one of the first things we looked at is, what's a random sample? How many different ways can you get a random sample? This is familiar. My sample size can't be any larger than 5% of the population. So if my population size is 1,000, then I can't have a sample size of over 50. Otherwise, the things in my sample might not be independent of each other. Now, almost always, I won't say always because I hate saying that, but in this class, we're always going to be sampling from a population that's big enough that this rule doesn't present a problem. Like it'll be, okay, citizens in the United States, or citizens of this town, or whatever, or the number of bobcats in a certain area of Wyoming, things like that, where the population is large. Okay, we've got to be dealing with a normal sampling distribution. And again, this is like chapter 8 stuff. How do we know that a proportion sampling distribution is about normal? Okay, I'm so glad you said that. You said if the sample size is at least 30. Everybody agree with that? Okay, we got one dissenter. Why not, Crosby? Yeah. This is easily confused now. We're talking about a proportion here. For the n to be at least 30 is dealing with the averages. So watch out. And like the lady says, if we take the sample size here and multiply it times p hat that we got from our sample, and then times 1 minus p hat, when we multiply all three of those together, the result needs to be at least 10. At least 10. And I want to point something out here. What we've done before is it's been n times p, and then 1 minus p. Why are we using p hat here? Anybody know? What are we trying to estimate? P. If I already knew P to plug it into this, we wouldn't be doing this. Right? So I'm basing everything on my sample. Now think about that. That's different for us. We're saying, based on what I got in this sample, I'm going to check to see if my sample is large enough. We don't know the population proportion, which is just P. Okay, here's what a confidence interval looks like. We've got p hat dead center. On the left-hand side, that's our lower boundary of the interval. This is in your formula pages. It says, how do you get that? Well, p hat minus this z a over 2. And that's actually in your formula pages. That z a over 2 is called a critical value. And then look what we're multiplying that by. Exactly, the standard deviation of p hat. And again, I'm using p hat in there, not p, because we don't know p. Look at the right hand. Look at the right-hand side. What changed? Yeah, the sign. I'm adding something to p hat to get the right-hand end. I'm subtracting something from p hat to get the left-hand end. That makes sense. P hat's dead center. Okay, the question might come up, well, how do you get that z a over 2 business? And there's a table in your formula pages that tells you how confident do you want to be. So you get to pick the confidence level. Here's what that table looks like. Notice if I want to be 90% confident, that critical value is 1.645, and that's what would replace the z a over 2. I just plug that number in. This is very mechanical, very mechanical. Now, Tuesday, next week, we're going to talk about, well, how do you interpret these things? But I just want you to just say, okay, I know how to make one. I might not know what it means yet, but I know how to make one. If I wanted to be, look at this, 99% confident, then that critical value is 2.575. And we'll see the results of that here in just a second. Stop right there. See if that makes sense. P hat's in the middle. I'm getting a left-hand end based on p hat. And I'm getting a right-hand end based on p hat. Okay, let's do one. Okay, so first thing I do, I get what p hat is. Now I know that it's x divided by n, so I've got 78 divided by 200. Easy peasy. You tell me when we get to something hard in this. Okay, when I figure that out as a decimal, because remember we're talking about a proportion, I get 0.39. So that's p hat. That's going to be in the center of our net. Then what? Well, do we pass all the requirements? Let's say we're getting this sample from a population of 20,000. Am I good? Thank you. Yeah, that's less than 5%. So that requirement's met. Was it random? Yeah. I left out the word random there, but let's assume it's random. What else do I need to know? Is the sampling distribution kind of normal? And look what I'm going to do. I'm going to plug these values in. Again, I'm using p hat. And what am I looking for? Exactly. Something greater than or equal to 10. And when I did it, this is what I got. So we can assume, and sometimes assumptions get us in trouble, but on this one, we can assume that our sampling distribution is normal enough. Might not be perfect, but it's normal enough. So then we can go ahead and build this confidence interval. Okay, so I'm drawing it out here. Notice I put 0.39 dead center. Now I just have to figure out where the ends are. So on this end, I know that's little, but it says p hat plus z a over 2. Now that a is really alpha, but we'll talk about that more later. And then inside the radical, I've got p hat times 1 minus p hat over n. In other words, the standard deviation. That's my right-hand end. I'm adding that amount to p hat. On the other side, same kind of deal, except I'm subtracting that from p hat. Now start plugging values in. There's nothing in there that is a variable. So on the left-hand side, these are the values I'm plugging in. 0.39 minus, where'd the 1.96 come from? Yeah, the chart. That's for a 95% confidence level. And I do the same thing on the right-hand side. And then it's just put in your calculator. And you can actually put those in there for each side just all at once. If you entered it in your calculator just like it's written there, you've got it. See if you get what I did. I got 0.322 for the left-hand end and 0.458 for the right-hand end. See if you get the same thing. The which? From that table. You probably didn't copy the table down, but that's where we got it from. It'll say 95% confident, and it'll have that value as the critical value. Now that table's giving you the most common ones. And Tuesday we'll look at, well, what if I wanted something that's not in that table? It's down there at the bottom of your Z-score chart. Okay, so that means, everybody getting the same thing I did? That means out here on the left end, I've got 0.322, and on the right end, I've got 0.458. There's our confidence interval. How would I write that thing? Well, I'd write it like this. There's our confidence interval. What's it mean? Let's say that we're trying to figure out what percent of this population likes the color blue best. Okay? That's all we're wanting to know. What percent of our population, we're trying to make a guess, what percent of our population likes blue better than anything? And I'm getting this right here. Well, our sample said, for that one sample, 39%. But our confidence interval says anywhere from 32.2% to 45.8%. Anything from 32.2% to 45.8%. That's our guess. Now, that's a pretty wide range. But look at what we're saying. We're 95% confident that our way of doing this captured the population parameter, meaning we think the true population parameter is somewhere between those two values. We're 95% confident. That's a difference of what, almost 14%. That's a fairly wide net. And we're going to talk next week about how do you make the net shorter and still be confident. What if I told you all, I'm 95% sure that on the next test, your grade's going to be between 10 and 100. Have I given you useful information? No. You're going to look at me like, what kind of idiot are you? See, we want something that we can use. In other words, narrow it down. When you hear polls in the news or on a news feed that you've got or whatever, and it says 84% of Americans feel this way about, and you fill in the blank. What else do they say? Plus or minus 3%. That's a confidence interval. If it's 84% plus or minus 3%, that means what? It could be anywhere from 81% to 84%. If I can't remember the number I said, but if I add it right. So anyway, they're giving you a range when they say that plus or minus. That's called the margin of error. And we're going to talk about that next week. They're just taking a guess. Okay, we look at this. When I subtract that, our actual interval is 0.136 wide. So it's 13.6% wide. That's how wide our net was. I just subtracted the small end from the big end. That's all I did. Okay, let's look at another one. It's starting off exactly the same, except now I want a 99% confidence interval. Everything starts off just exactly, I just copied this from the other page. Up to here, it's exactly like what we just did. There's going to be one thing that changes here. The confidence level. And so instead of plugging in 1.96, I'm plugging in 2.575 from the table. For a 99% confidence level, notice that number got bigger. It was 1.96 for a critical value. Now it's 2.575. I'll let you think about that for a minute. What's that going to do to our interval? Make it smaller or bigger? Bigger. That just makes sense. We're throwing a wider net out there. I can be more confident. All right, so I plug that into my calculator. You don't have to do this. I already did the work. But here's what I got. 0.301 for the left-hand side and 0.479 for the right-hand side. So I put those up there. If you compare it to the one we just did, let's go ahead and figure out this difference. I'm getting that. 17.8% wide. The other one, if we look back, was 13.6. This one, with 99% confidence, is 17.8. The net got bigger. It's logical. The bigger the net, the more confident I am that somewhere in that net, I got the population proportion, the true population proportion. If I only had an 80% confidence level, the net would get smaller. Okay, anybody have a question? This is where we're going to stop today. We're going to pick up there next Tuesday.